So hello, in the second section for the strength of material interview preparation part 2. So here we have the other task called section loading. So if you are given such a case that where a material, a slab, a bar like thing is loaded at separate sections, then they are asked to find the stress induced in the BC section. So for this thing, what we need to do is we have to do the free body diagram of the separate sections. So we have to start first, place the diagram A, B, C, D, and D, and start from the beginning and the end. So for the AB section, as you can see, the outside is 10 newtons, and the same will be induced on the other side as 10. And for this CD, the outside is 30 newtons, and the in this section the same load will be induced, equal and opposite reaction. But when we are drawing the center part, we need to mark the loads in such a way that this combination of these two loads will result in this. So for example, this side that is 30, so we have to make it 20 this side. That way, if you add the both, in the resultant load will be in the left side. The same way goes to here. If you put a 20 newton load, the overall load will be on the right and left side as 10. So in this case, we can see that the BC section, you can see that if you want to stress in this BC section, then the stress will be 20 newtons, which is this, divided by the area. In the second part, they will give a material with different areas and different lengths. So we have to find the elongation. For example, if you want to find the elongation at the BC, then it is simple. Take this section out, and as this load is not varying, it is same. So same thing happen in this section. The load will be P, and the area A2, and the length is L2. So for the stress, it will be P by A2, and the strain will be sigma by E, which is P by EA2 from this, and as a result, delta L, which is the elongation, will result as this formula PL by EA. So simple. But the third one is the uniformly tapered bar. That means the area is uniformly varies uniformly till this here, and we need to find the elongation of this bar. But what to do? To find the elongation of the bar, we need to know what is happening, because the stress is changing uniformly throughout this area. So for this thing, we need to find the diameter at a particular given distance. So for example, at a distance x, what is the diameter here? So if you know the diameter here, we can find that the stress at this particular point. Then we can integrate this to find the elongation. For example, so to find the diameter here, that is dx, we need to use this unitary formula. That is, the dx is d1 minus this formula, d1 minus d2 by L times x. If we use this formula, we will find the diameter at the given x distance here, this. So at this particular segment dx, we will find the elongation. So the area at this dx will be this pi d squared by 4, and the stress will be P by the area. So same thing is here. The strain will be using the same formula. We will find the strain, and the elongation, that is delta x by the original length, that is dx, is given. So the delta x will the elongation will be this. If we integrate it for the whole length 0 to L, we will find the elongation for the uniformly tapered bar. So next is, what do you understand by the composite section and the loading of the composite section? So composite section means the material which are combined or placed in such a manner that they are parallel to each other. So there are two ways. One is to make a coil around each other with equal length, and the other one is to place the material parallel to each other. So it is basically why we need this such a composite section, and why are they created? These are created because to carry more load than the normal one. If you have a combination of material like this, it can carry more load, and there are only two cases, and the total load carried is distributed accordingly, because the material strength of these materials are different, so thereby the force they are carrying will also differ. And as the length is same, this material are arranged in such a way that the change in the length will also be same. Then if you want to find the stress, as the elongation is change, as the elongation is same, therefore the strain will be same. In that manner, the ratio of the stress by elasticity, the ratio of this of the both the material will be same. So it goes to the same thing, the stress of one and the area of one, stress of two and stress of three. This is the equation. So the other question is, when we heat this composite section, what stresses are induced? So we have such a combination of a composite section, and if we heat this two material, initially this is the state. When this there is no bonding here and they are free to move, free to elongate, you will see that this the left side the brass material is there, right side is steel material is there. As you know, the thermal coefficient of the brass is higher than the steel. That means the brass will expand much further than the steel. So if you allow it to elongate freely, then the brass will elongate fast more than the steel. But the thing is that as they are composite section, they are bonded in such a way that this brass, although it extends much, it also pull the steel above, and while the steel's thermal coefficient is less, this steel will pull down the brass expansion in such a way that the overall expansion of this composite section will be in the median of this individual expansions. So this thermal expansion happens in such a way the brass feels the compression because the steel is pulling down, and while the steel feels the tension because the brass is pulling the steel bar up. So these two kinds of stresses are induced in this composite section. So the next question is, derive the expression for the elongation due to the self weight of the bar. So this is a self weight, the bar is hanging, it is attached here. So from this diagram we can see that the stress along this bar will be highest here and the lowest down there, because this is there is no load here, there is no hanging thing. So the stress will vary from here to here, 0 to maximum will be there. So if you want to find the elongation of this whole bar, then we need to know the weight at this particular point. So for example, let's say at this section dx, we need at this point we need to find the stress. Then we need to know the force which is hanging here. That means the weight of this portion should be known. So as we don't know particularly what is the weight of this portion, we need to know the specific weight of this whole material. So to calculate the stress, then we need to have the weight of this portion. So for that we need a specific weight, and the specific weight is nothing but the total weight divided by the volume. So the total weight W by volume is AL, and it is also equal to the density and the gravity, which is constant basically. So the force at a dx will be specific weight times the area of this section times the length. So this is basically A times X is the volume. So specific weight times the volume will give the total weight of this portion and also the force of the portion. So stress is nothing but the P by A. So when we equate it, we will get WS, specific weight times the X, and the strain using the formula we will get this expression, and for the elongation delta X we will have this expression. Then the other question is, why bulk modulus is called so? As we know the bulk modulus formula from the earlier section, that K is equal to minus delta P by volumetric strain. So as we know that if the pressure increases, the volume decreases. So basically dP is nothing but the change in the excess pressure. So for the ideal cases, ideal case for fluids or gases, the PV is equal to MRT. If this is a constant, then pressure is inversely proportional to the volume. So the pressure happens due to the intermolecular collision between the fluids, which is only happens in the fluids, not in the solids. So basically that means the pressure is relevant to the fluid, and as the fluid shows the bulk property, thus this modulus is called bulk modulus. And K, this bulk modulus is also used for solids. In that case, the change in pressure is changed to the change in compression, because pressure is nothing but which is relevant to the fluid, and the change in compression is relevant to the solid. So that means this bulk modulus is also used for solid cases. And it is commonly said that liquids are mostly incompressible, but this depends upon the situation. Incompressibility happens due to the change in temperature or the pressure, or in which this changes the density of the material. When the density of the material changes, the compressibility changes. So for liquids, the bulk modulus formula is this, and as we know that compressibility is inversely proportional to the bulk modulus. If the compressibility is 0, the bulk modulus is infinity. Okay. Okay. For example, if for such some given cases the density doesn't change, that means initial and the end density, final density is same. That means the bulk modulus will be infinity. That means the liquids becomes incompressible, even though incompressible in normal situation. But in normal situations, salt can be compressible, gases can be compressible, but liquids are incompressible. So other question is, what is complementary shear stress? So complementary shear stress is a stress which is basically self-induced, or it happens automatically if we don't have to do anything. It's like complementary food or something like that. So when we discuss about the normal stress, that is basically tensile or compressive stress. So for example, in this case, a cantilever which is pulled here, there is a tensile stress happening in this inside this free body diagram. So you can see when you have force like this, the stress is induced. Stress happens here. Also, automatically to make the material in equilibrium position, uh, equal and opposite tensile stress is induced to, and in this case this makes this whole body in equilibrium. But for shear stress, which is basically parallel to the surface, when we have such a force, there's a shear stress happening here, and in reaction in the bottom also the shear stress is happening here. But the complementary stress is also plays here, automatically comes and it acts along this reaction. So if we have this only two forces, stresses here, this means the body will rotate and it's not in equilibrium, but in reality it doesn't happen. So to make this body in equilibrium, the body automatically creates this complementary shear stress like this, which basically keeps the body in equilibrium. So when you have a case like this in cantilever, as you can see, the force acting here, the shear stress happens here as a reaction force. The shear reaction also happens here. In this case, as you can see, the complementary stress happens here on this up and down faces. So now this body will be in equilibrium. Okay. So the other thing is stresses on oblique plane. So for a given body such as this, if the forces are applied, what is the stress on this plane at given angle theta? So if you want to know the stress at this point, we need to uh, separate this section, and we need to find what is the force on this plane, on this AC dash plane. So we can get the normal force on the tensile force with the formula. So the normal force will be F of cos theta, and as you know, the stress at AC dash, normal stress will be Fn by AC. So if you want to know the area of this thing, we can get it from here. So we know this area AB, we need to get the AC. So the AC is nothing but AB by cos theta. So from this thing we can get that stress at AC will be F by AB times cos square theta, and F by AB is nothing but the normal stress in this AB plane. That means stress in AC dash is equal to stress in AB plane times cos square theta. So in simple manner we can say that the normal stress on this oblique plane will be stress along the x-axis times the cos square theta on the oblique plane. So why we need these stresses on the, why we need to know the stresses on the oblique plane? We need the normal stresses to check the maximum stress on any oblique plane to verify that it doesn't precede or exceed the yield strength. So for a working model, for working safe material, we should make sure that the normal stress on any given plane is less than the yield stress, so that we can avoid the failure of the material. So the next question is, what are principal stress and principal plane, and what are their significance? So for a given material like this, so a plane at which the normal stress is maximum or minimum is called principal plane. And when we at any given plane, if we have a maximum normal stress, it is called sigma 1, and minimum normal stress is called sigma 2. These are two called principal stresses. So as we need to know that both these principal stresses are perpendicular to each other, and this wherever the principal stress is happening at that plane, the shear stress is always 0. So we need to know the principal stress and plane to compare it with, again, with the yield stress. Always the principal stress should be less than the yield stress by safety of factor, to keep the material away from the failure situation. So always the normal stress should be less than the yield stress, and the shear stress should be less than the shear strength. Okay. For normal materials, the shear strength is equal to the half of yield strength for normal materials, but it differs for the brittle and the ductile material. So what is the basic difference between the brittle and ductile material are that they have very good shear strength for brittle material. These have a good tensile strength. Brittle material have poor tensile strength but good compressive strength, and ductile material have poor shear strength. The reason is that, as we know, for the normal material this is the situation, but for the ductile material the shear strength is less than the half of the yield strength, while for the brittle material the shear strength is more than the half of the yield strength. So in this situation we can note that they have better shear strength, they have lesser shear strength. So this is basic difference. Thank you.